right. Well, so I want to thank everybody so much for joining us this morning. Today we have a really exciting talk from Laura Larocca, who is assistant professor with the School of Ocean Futures at Arizona State, talking about Greenland-Wide accelerated retreat of peripheral glaciers in the 21st century. So thank you so much for being with us.
Thanks, Megan, for the introduction, and thank you for the invitation to speak this morning. It's really my pleasure to talk to the Climate and Cryosphere group. So today, I'll talk about some recent work which first aimed to document the response of Greenland's peripheral glaciers to climate change over more than a century, and second, to place that retreat of these glaciers over the past few decades into that century-long context for the first time. So we were really interested in answering the question, how unusual or unprecedented are these recent changes in these smaller ice masses that dot the coast of Greenland? So to go about answering this question, we used a few really unique observational data sets, one of which is a set of Danish historical air photos. And you could see in the background photo here, I'm just showing some of the Danish pilots in an open cockpit plane that they used to collect photos of Greenland in the 20th century. And the aerial photos collected during these mapping expeditions of the coastline really represent the only robust, widespread observations of 20th century glacier change for the vast island of Greenland. So before I get into the work, I'd like to just start by acknowledging all my amazing co-authors on this work. So I actually started this project when I was a PhD student with Yarrow Oxford at Northwestern University. And Anders Bjork was also on my committee from University of Copenhagen. And Anders really pioneered the use of these air photos for answering some of the scientific questions that I'll get into. I'd also like to acknowledge Max Twinningward, who led the data collection in Northern Greenland, and also Avril Schweizenberg and Jason Briner from University at Buffalo, who led the data collection in Western Greenland. And then others from University of Copenhagen and the Geological Survey of Denmark. So this study would really not have been possible without this international collaborative effort and access to the images at the Danish National Archive. And there are also hundreds of hours of analog photo processing by myself and several people that I've listed here. So it was really truly a collaborative effort, and it was 5+ years in the making. So I'm sure everyone here is aware, over the past several decades, temperatures in the Arctic have increased substantially more than global temperature. And this plot here shows annual mean temperature anomalies in the Arctic, so those darker colors, compared to globally, these lighter colors between 1950 and 2021, derived from 4 observational data sets. And these data show that the Arctic has warmed almost 4 times faster than the global average from 1979 onwards, a phenomenon also often referred to as Arctic amplification. So in response to this increased temperature, glaciers globally are, of course, shrinking and losing mass. This figure shows regional and global mass change rates with a time series of mean surface elevation change rates for the world's glaciers, and also broken up into the 19 first order regions of the Randolph Glacier Inventory. And in the first 2 decades, which is the period that this study covered of the 21st century, Greenland's glaciers together lost mass at a rate of -35 gigatons per year. And the only region that outpaced that was Alaskan glaciers and ice caps. So mass loss from glaciers and ice sheets are contributing to global sea level rise. And although they're much smaller in area and volume as compared to the Greenland ice sheet, glaciers peripheral to the Greenland ice sheet are actually really important contributors to global sea level rise. And as shown here in the map on the right, and also in this table from a recent study by Kahn et al., glaciers peripheral to the Greenland ice sheet constitute a really small portion, just 4% of Greenland's glaciated area, but they now contribute a disproportionately large percent of the island's current ice loss, about 14% of that total loss. So the global retreat of glaciers is a prominent indicator of this ongoing anthropogenic warming. Yet our ability to evaluate contemporary glacier loss within an extended temporal context has remained pretty limited, as observations of glacier change before the satellite era are pretty sparse. And this is partly owed to their remote and logistically challenging settings. And so direct field measurements on glaciers in Greenland are even more rare. So for example, among Greenland's 20,000 glaciers, just one glacier has ongoing mass balance measurements, and those begin just from the mid-1990s. And so this really limits our understanding of glacier sensitivity to climate change, and it also limits our understanding of the degree of unusualness of these very recent changes that we're seeing. So in recent years, historical data sets have proven a valuable resource in filling some of these observational gaps. So for example, rediscovered or declassified photos from aerial campaigns or early satellite missions have been utilized. And I'll talk a little bit more about these two data sets that were used in our compilation in the next few slides. So the Corona satellite and these Danish aerial mapping expeditions. So the Corona program was a series of American satellites produced and operated by the Central Intelligence Agency, and they were used for photographic surveillance of the Soviet Union and other areas beginning in 1959 all the way through 1972. And this is a unique satellite system because film was actually retrieved from orbit via a re-entry capsule that was named Film Bucket, designed by General Electric. And so this film bucket actually separated from the satellite and fell to Earth. After re-entry of the film bucket, parachutes deployed, and the capsule was actually intended to be caught mid-air by a passing airplane, which you could see a photo of here. It could also land at sea, and if it did, a salt plug in the base would dissolve after a few days, allowing the capsule to sink if it wasn't picked up by the US Navy. And so these images were declassified in the 1990s, and they actually have been pretty widely used for historical Earth observations. So next I'll talk about these Danish air photos. So in the early 20th century, several expeditions were launched in Greenland to produce new geographical maps, or in many instances to map the coastlines for the first time. So these photos I'm showing here show some of the Danish pilots and the open cockpit Henkel planes that they used to survey East Greenland in 1932. And the photographs were captured with a rotating camera, and they flew at pretty high altitudes, around 4,000 meters. So after the initial use of these photos, they collected tens of thousands of them. They were classified and generally not accessible. And they actually laid forgotten in a 17th century fortress outside of Copenhagen until 15 years or so ago, when Anders Bjork, a co-author on this work, first came across them. And Anders knew that these photos might provide a really unique opportunity to observe changes in Greenland's glaciers at pretty high spatial resolution from a period really when quantitative observations and measurements are absent. But it took him many years to sift through all of these negatives to work out which of these photos might be useful for some of the scientific questions that we would like to ask. So as he extended his search, he came across many more images taken during Danish and US Greenland aerial surveys from the 1940s all the way through to the 1970s. And so together, this air photo collection includes about 200,000 photographs. And you can see in these figures of Greenland, the flight lines and the blue lines of where the pilots took photos in each of these periods. There was also Danish mapping expeditions that were carried out from 1978 to 1987. So an additional 3,500 vertical photos were acquired during this time, and they were used in 2016 to produce a really high resolution 2-meter orthophotograph. And this is the data set that we use as our reference, and I'll get into that a little bit more later. And so together, all of these collections provide us with invaluable pre-satellite era observations, and they allow us to extend the duration of the observational record of Greenland's peripheral glaciers. So these historical data, just to give you some context, were first utilized in a 2012 study that documented the response of 132 glaciers to climate change in Southeast Greenland over 80 years. And the study found relatively high retreat during a period of warming in the 1930s and also in the 2000s. It also showed that many land terminating glaciers underwent a more rapid retreat in the 1930s than in the 2000s, whereas the marine terminating glaciers retreated more rapidly during this recent warming. In 2018, Anders and others used historical air surveys and the SPY satellite imagery and also remote sensing products to map the length fluctuations of an additional 350 peripheral glaciers and ice caps in East and West Greenland since 1890. And they showed that regional changes in ice volume as reflected by changes in glacier length are related to changes in precipitation associated with the North Atlantic Oscillation. So they found that positive phases of the NAO increase accumulation and lead to glacier growth in the eastern periphery, whereas the opposite effects were observed in the western periphery. And they also suggest that with projected trends toward positive NAO in the future, the eastern peripheral glaciers might remain relatively stable, whereas the western peripheral glaciers might continue to diminish. And then finally, a pretty recent study from 2020 utilized these historical data to estimate ice mass change between 1880 and 2012 for Greenland's 3 largest outlet glaciers, Jakobshavn, Kangerlussuaq, and Helheim. And this study found that the amount of ice lost during this 130-year period is pretty comparable to the projected mass loss by 2100 under the worst case scenario, where the temperature change is estimated to be 4 times larger than that which took place since 1880. And so this really strongly suggests that these future projections of mass loss from these 3 glaciers are severely underestimated, and that their contribution to sea level rise could far exceed that worst case scenario set out by the IPCC. So I think these 3 studies together really clearly demonstrate the importance of long-term observations in improving our understanding of glacier sensitivity to changes in climate. So just to sort of summarize the motivations behind this work, long-term records of glacier fluctuations first provide us with context for recent change, and they also provide us with some constraints for future change and a way to evaluate future projections. And as I've shown, there are a pretty limited number of glaciers that have any 20th century observational records, and only in a few regions of Greenland. So we ultimately decided that a Greenland-wide view was needed. So we took this opportunity to extend the limited time frame of glacier records across all major regions of Greenland. So I'll just summarize the project here and then get into some of the methods. So we combined satellite observations with these underutilized aerial photographs to document the evolution of more than 1,000 individual glaciers over a 130-year time frame. So specifically, we mapped the ice front positions of 821 glaciers in South, North, and West Greenland. And then we extended 364 existing records of glacier length change that began in the early to mid 20th century from the southeast to the northwest and the northeast. So our observations cover all of Greenland's major regions, and this work more than doubled the number of glaciers in Greenland with detailed air photo-based 20th century records of their length fluctuations. And importantly, this effort enabled us to contextualize the Greenland-wide magnitude of 21st century glacier retreat within this century-long timescale for the first time. So now I'll talk a little bit about our methods. So we focused our study on glaciers that terminate on land and that are distinct from the ice sheet, so that is physically detached or dynamically disconnected. And these glaciers are fed by local precipitation, and they're primarily sensitive to atmospheric climate variability and respond quickly to climate shifts. So this just shows a schematic of all of our data sources used in our compilation. I'm just showing 3 of the aerial photos from South Greenland here. They were just gorgeous photos to work with. And then to further extend our records to the turn of the 20th century, we also documented ice extents based on geomorphic evidence, so terminal moraines, which mark their maximum extent during the Little Ice Age. And for the air photo and satellite imagery data collection years, those were just based on the availability of quality late summer, low cloud, and low snow cover imagery. So you might be wondering, why hasn't this been done before? So although these historical data offer invaluable insights into glacier status before the widespread use of Earth observing satellites, documenting past glacier states from this aerial imagery is pretty difficult and requires a labor-intensive process that currently can't be automated. So this mapping, as I mentioned, is the result of substantial archival work, so including digitizing the photos, orthorectification, georeferencing of thousands of these paper copy photographs from the Danish National Archives. So here on the left, I'm showing how the historical air photos were scanned and digitized from paper copies. We did that on a Canon precision scanner. And this image here shows an example set of overlapping 20th century historical photos that were scanned and digitized in 2018. And for our purposes, we selected vertical only photographs for use. So we did not use oblique photographs, an example of which is this first one here. So once in digital form, the historical air photos were oriented, rectified to a standard shapefile using the image fiducials and cropped in ArcGIS. So that is what you see in this top panel A. And then we generated orthophotos to remove the terrain distortion from each of these overlapping sets of historical images. And that resulting orthophoto is what you see in panel B there. All orthophotos were georeferenced in ArcGIS using tie points near the glacier fronts, and we co-registered the air photos with that high-resolution 2-meter orthomosaic product that I had mentioned earlier. And again, we use that as our reference data set. So the glacier fronts in the 20th century historical imagery and in the satellite imagery were manually digitized as polylines at the transition from ablated ice to bare bedrock, and the Little Ice Age maximum extents were digitized using that high resolution 2-meter orthophotograph. So this figure shows the front retreat of an example glacier in southern Greenland between 1900 and 2021. So to calculate the frontal change rate in meters per year between the fronts, we used a few different methods. So the first is shown here in A, the multi-centerline method, and this method quantifies the front change between each observation every 10 meters across the entire glacier margin. B here is the centerline method, and this method quantifies the front change between each observation along the glacier centerline. So in other words, the frontal change rate is calculated by measuring the straight line distance between point features divided by the number of years between the observations. And this last panel here, C, is the method that we use to extend our data sets where we had some information from the 20th century already from the southeast, northwest, and northeast. And again, we extended those to present. So the front change here for the most recent subperiod, X, equals the total length change between the late 20th century observation and present, which is Y, minus the sum of the length change that occurred in the previous two subperiods, Z1 and Z2. So the frontal change rate for the most recent subperiod is just calculated by dividing the total length change X by the number of years between the two final observations. Okay, so now I'll move on to our results. So here in this figure, I'm showing the frontal change rate in meters per year for glaciers in our 8 regions divided into observational periods. So you have frontal change rate again on the y-axis and time on the x. The error bars represent the combined measurement error, and the increased transparency here in the 6 reported post-Little Ice Age rates signify their higher uncertainty because we have pretty poor constraint on the timing of Little Ice Age deglaciation across Greenland. The dashed black lines show the mean frontal change rate across all observations in the 20th century and the 21st century. So over the full 130 years of observation, we see that Greenland's land terminating glaciers have undergone quite substantial and widespread retreat. And although we observe retreat over the full observational period, the acceleration in recession in the 21st century stands out as distinct. So across all 8 of our regions, the mean frontal change rate during the 21st century is roughly double that of the 20th century. And this marks a major transition into a new and rapid state of downwasting. Further, despite the wide range of climate zones and glacier characteristics that we have across Greenland, we find that this recent accelerated retreat is ubiquitous, so including Earth's most northernmost glaciers. So in addition to the length changes in absolute terms, we also calculated 21st century length change in relative terms. So as the percentage of the length lost relative to the late 20th century length. And again, we use that common data set, the orthophotograph, to measure that late 20th century length. So over the last 2 decades, we find that South Greenland's glaciers lost more than 18% of their total late 20th century lengths, while glaciers in the other regions lost between 5 and 10% of their total late 20th century lengths. Our data also suggests that recent retreat is largely unprecedented in over a century. So first, of the glaciers that we studied with at least 2 observations, 1 in each century, the highest rate of retreat on record occurred within the 21st century for almost 90% of them. And then second, of the 6 regions with records beginning around the turn of the 20th century, so that is 1890 to 1910, which I've marked with stars, the regional frontal change rate in the most recent observational period is unmatched in more than a century in all but 2 of the regions, the South and the Northeast. So just zooming in on those regions, in the South, post-Little Ice Age retreats have been nearly matched by recent loss, so within error. And so the major exception here is the Northeast, where retreat rates in the 21st century have not yet exceeded the rate of retreat in the early 20th century. However, in the paper, we do argue that these periods are not directly comparable in terms of measurement uncertainty, climate, or glacier hypsometry. So first, the uncertainty in the reported post-Little Ice Age rates is higher because, as I mentioned, constraint on timing of the Little Ice Age deglaciation isn't well constrained across Greenland, and our glacier front position is inferred from undated geomorphic evidence. Second, high rates of retreat post-Little Ice Age can be in part explained by differing glacier area elevation configurations. So for example, some glacier fronts would have been situated on much flatter and lower elevation terrain than at present. So this implies a higher sensitivity following the Little Ice Age maximum, as comparatively more glacier surface area would have been exposed to ablation with a comparable temperature rise. We also note that some studies, notably those that use cosmogenic exposure dating of glacial moraines, generally suggest an earlier and very variable Little Ice Age maximum timing across Greenland. So in this case, an assigned age of 1900 for the timing of little deglaciation in the south, or 1910 for the northeast, would result in artificially high retreat rates for that first observational period. So in other words, if the onset of Little Ice Age deglaciation occurred earlier than we had reported here, making our earliest observational periods have artificially high retreat rates, this would ultimately bolster the conclusion that 21st century retreat is pretty exceptional on this century timescale. So we also assessed glacier response to changes in climate by comparing regional frontal change rates with long-term weather station records, as well as catchment-specific climate and surface mass balance output from the MAR regional climate model. And surface mass balance is the difference between accumulation and ablation of snow and ice on the surface of a glacier. So specifically, we looked at summer temperature and accumulated precipitation from 7 stations with long-term observations that were closest to our 8 regions of interest. In addition, we extracted summer air temperature, snowfall, and surface mass balance annual sum between 1950 and 2019 from MAR. And MAR is forced at the boundaries with ERA5 atmospheric reanalysis, and we use the monthly mean values downscaled to 1 kilometer, and we took an average of the variables over each glacier catchment. Finally, we also collected information on glacier-specific characteristics, including elevation, area aspect, and slope from the Randolph Glacier inventory. And we calculated regional hypsometry using the Arctic DEM and also the glacier polygons from the RGI. So here in A, I'm showing, again, the locations of all of the glaciers that we measured in the black dots split up by regions, which are denoted by the different colors. And the DMI stations are noted in triangles here. In B, here is the plot you've seen previously, so the frontal change rate in meters per year for our 8 regions. C is the summer temperature anomaly from our 7 weather stations, and bars are the 10-year mean. Here I'm showing winter half year accumulated precipitation from our weather stations. And then finally in E, we have the regional surface mass balance anomaly from MAR. And the bars are the 10-year mean of the annual sum. So the overall picture that we see here is that we find that regional trends in climate and surface mass balance from MAR agree pretty well with our frontal change rate measurements. And this confirms that these glaciers are rapidly responding to climate changes via adjustment of their front positions. So just as an example here, just comparing the first 2 decades of the 21st century, we find higher rates of retreat showing on the left and more negative surface mass balance anomaly here on the right in the most recent decade compared with that of the first decade of the 21st century. And we see this for glaciers in the southern region, in the northern region, in the southeast, in the northwest, and also in the 3 other western regions, so Central West, Southwest A, and Southwest B. Conversely, glaciers in the northeast experienced a lower retreat rate and a less negative surface mass balance anomaly in the most recent observational period compared to that of the first decade of the 21st century. And here I'm showing surface mass balance anomaly by decade, and again, colored by region. And when looking at the most recent decade alone, we see a notable divergence in both the rate of retreat and surface mass balance between glaciers in eastern and western regions of Greenland. So most dramatically between Northeast Greenland in the light blue and Southwest Greenland in the yellow and olive colors. So the eastern regions are showing a less negative surface mass balance and less retreat, and the western regions a more negative surface mass balance and more dramatic retreat in this most recent decade. So we looked further into the climate patterns, hoping to understand what's driving this east-west divergence. So the left plot here, I'm showing summer temperature anomaly and snowfall anomaly by decade, again colored by our 8 regions. And this shows that while summer temperature has generally increased across all regions over the past several decades, of course, with varying magnitudes of change, there is higher regional and interdecadal variability in precipitation. The right plot here, I'm showing spatial trends in summer temperature and snowfall, the annual sum for just the period 2010 to 2019. So reds here indicate warmer, and here the blues indicate wetter, so more snow. So together, these climate data suggest that the east-west divergence probably reflects higher snowfall in East Greenland and drier conditions in West Greenland in this most recent decade. And other studies have actually observed similar slowdown in mass loss from glaciers around the North Atlantic over the last 5 to 10 years. So these plots are from a recent global study which ascribed this slowdown to cooler, wetter conditions in the region over the last decade. So they found that record thinning rates, for example, of Icelandic glaciers between 2000 and 2004 were nearly halved during the 2015 to 2019 period. And this also coincided with decelerated thinning of Scandinavian glaciers. So taken together, they suggest that the slowdown in mass loss from these regions, in addition to Eastern Greenland, might define a regional pattern, and they refer to this as the North Atlantic anomaly. I also wanted to point out, though, despite the regional increase in snowfall in East Greenland in the most recent decade, we do find a pretty high rate of frontal change in the southeastern glaciers in the most recent decade. So this suggests that the increase in accumulation in East Greenland was not sufficient to impede retreat of glaciers in that particular region. And we think this could in part be because of differing hypsometry between glaciers in the northeast and southeast. So as you can see in this figure here, the majority of the area of the southeastern glaciers are located at lower elevations, whereas the majority of area of the northeastern glaciers are located at much higher elevations. So now I'll just provide sort of a general overview and get into some key takeaways. So our study provided the first comprehensive picture of glacier retreat across all of Greenland's key regions over a century timescale. And this really allowed us to contextualize the Greenland-wide magnitude of 21st century glacier retreat within this century-long timescale for the first time, and really get at that question that I introduced in the beginning of the talk, which is how unusual are recent glacier changes. And I'll just go through what I think are the major take-homes of the work. So we observed a notable shift into accelerated retreat in the last 2 decades, and glaciers in Greenland are now retreating at roughly twice the rate observed over the 20th century. And despite the wide range of climate zones and glacier characteristics across Greenland, we find that this recent accelerated retreat is largely ubiquitous. So this is occurring even among the northernmost glaciers in Greenland. I think our work also provides enhanced confidence that recent changes are largely exceptional on a century timescale. So in other words, for most regions, we find that the rate of retreat observed in the 21st century is unprecedented when viewed within this lengthened century-long context. We also point out that with continued rise in greenhouse gases and further warming, these already exceptional rates of retreat are likely to be exceeded in the coming decades. Our study also shows that these glaciers respond pretty quickly to climate shifts. So in other words, it really reinforces that our choices and how much we decide to reduce our emissions matter. Every incremental increase in temperature will have significant consequences for Earth's ice. And so a takeaway could be that swift action to limit global temperature rise will reduce their future loss and contribution to sea level rise. Finally, I think the loss of these smaller glaciers can also be thought of as an early warning system or a way to anticipate the effects of climate change on Greenland's central ice sheet, which holds enough water to raise global mean sea level by more than 20 feet. So I just wanted to wrap up here by providing some links. So the paper is open access if you'd like to read it. We also wrote up a research briefing, which is a new short format for communicating the main takeaways of research papers to readers. And this is offered by Nature Climate Change. And there was some media coverage of the work. So it was covered in the New York Times, which was a real dream for me being a New Yorker. And it was covered along with another paper that Anders was involved with at the time that looked at changes in Greenland's last remaining ice shelves in northern Greenland. So with that, I'll wrap up. I will be seeking grad students and postdocs in my lab in the coming months, so please do reach out if you're interested. And thank you. I'll take any questions.
Thank you, Laura. That was an extremely so interesting to talk. There are already a bunch of questions in the comment section. I don't know if people want to just chime in and ask them directly, or I can read them out.
Sorry, I don't know how to raise my hand. This is Keith. May I speak?
Yeah, of course.
Yeah. Thank you, Laura, for the really excellent talk. I typed 2 questions into the chat and I'll just repeat them here.
Okay.
Keith Algerson from CliC. The first was you showed a great use of those old US reconnaissance photos from the Cold War period. And I'm just curious, I guess that the Soviet Union was taking similar reconnaissance flights all over the place, and whether there's any chance or you know of anybody who's trying to find similar reservoir of old photographic evidence from the Russian side. That's my first question. And my other question is, next year, you may have heard the United Nations has declared International Year of Glacial Preservation or Glacier Preservation. And I don't know what such a year can do, but you've described very, effectively that we've got a pretty disastrous lack of glacier preservation in Greenland. Is there anything you can think of that we as CliC or as an international community should be doing in that year, using that year that would be beneficial to the situation you've so eloquently described? What can we do in such a year? Thank you very much for your talk.
Thank you, Keith. Those are both really great questions. Yeah, I had the same thought about what was going on the Russian side. I think Anders would probably have some more information. I think he's looked into that, and I do think there are many hundreds of thousands of photos on the Russian side, but I don't think that there's any chance, especially now, of us being able to utilize those for science, unfortunately. And then for your second question, what can we do in the year of glaciers? Yeah, I think one thing that might be interesting is maybe getting together as a community and discussing how we might get all of these photos digitized, because I think there could be much more work done. As I mentioned, I only looked at 1,000 glaciers in Greenland, and there are an archive of 200,000 air photographs. And so if we could figure out maybe how to digitize these in some automated way for even public use, I think that would be a wonderful thing to do as a community. But I'll think about that question more. That was a great question.
Edward, I think you had a couple questions.
Yes, thank you very much. Can you hear me?
Yes.
So thanks for that great talk, Laura. Also a great data set as well. It's just fantastic, and I think that's going to be incredibly useful to well, it probably already is to the wider community. So I guess an obvious question, and the Anne's echoed it in the chat, is what's the current status, please, about the availability of these data to the wider community? Because obviously they're very hard-won data, and obviously, you know, your team obviously has to, you know, make sure you obviously publish what you need out of that first. But is the plan to make them available, if they're not already, to the wider community? Because it just seems a real treasure trove, doesn't it? So that's one question. Then the other question I had is about your regional retreat, the recent retreat of glaciers in different regions of Greenland. It seems from some of your results that you showed that there are some time differences between different regions, and Leanne's also commented on this in the chat as well. But also for a later plot you showed, there's been, it looks like there's been an increased variability in the surface mass balance in that last decade, which is quite interesting, because obviously we're still getting a lot of mass loss. But as you say, in certain parts of Greenland, having maybe increased precipitation or increased variability of precipitation between successive years is giving you a real jumps, isn't it, between the SMB? So this sort of sensitivity of the whole system increases. So I found that a really particularly interesting result. So thank you again. Yes, just those two things really.
Thank you. Yeah, so as far as the availability of the data, we did actually make the data available when the paper was published. So those data are available at the Geological Survey of Denmark and Greenland have an archive. And so all of the frontal change rates are available through there. And then we also made available all of the data that we extracted from MAR. So you could see climate and surface mass balance as well. So that's all publicly available. That was really important for us to do. And then as far as the variability that you pointed out between regions in the last decade, that was really, we found that result to be really interesting as well. So I mentioned in the beginning of the talk that Anders Bjork had written a paper in 2018 that suggested that this difference between the East and West was linked to the North Atlantic Oscillation. So that's something that could be interesting, I think, to look into further in the future. And is this pattern going to continue? We really don't know. So I think that that's a great question that we'll have to keep monitoring these glaciers into the future and look at that again.
Thank you. And I guess you could also use the, well, you may already have done this, more regional measures of air circulation change, like the Greenland Blocking Index or something like that, which some other studies have suggested is more strongly correlated, at least, with some of these local glacier changes. But thank you again.
Yeah, I think that would be a great follow-up study. We had so much data to fit into the short form paper that we didn't end up looking into these patterns as much as I think that we could have, but I think that would be a great follow-up.
Thank you.
Thank you.
And I think Ray Bradley has a question.
Hi, Laura. Thanks a lot. That was a fascinating talk. And as you were talking, I was glancing at the paper and the supplementary information from Nature Climate Change. But I wonder if we wanted to look at a specific location. I'm working in northern Greenland. How can we access the photographs, the sequence of photographs for a specific geographical spot? We have to contact you directly, and or is there a database somewhere we can sort of click on?
So I don't believe that there's a database right now, but I think that's something that would be really useful to have as a community in the future if we could figure out how to build that. But I do have a shapefile of all of the locations where photos are available around Greenland. So you could definitely email me and I could take a look if there's anything available for that particular location. And then the next step would probably be to contact Anders, and usually, unless you're lucky, the photo hasn't been digitized. So that would involve maybe Anders going physically to the archive, finding that group of photographs and then scanning them in, and then sharing.
Okay, thanks. And one other question about changes related to the driving factors. Have you looked at the sea ice extent, or rather open water extent, particularly around the north and northeast? Is that a factor affecting mass balance?
That's a really great question. We didn't look into that, but I just wrote up a paper looking at snowline changes across the Arctic, and we actually did look. We calculated a metric for new open ocean, basically, and we only found that glaciers in Alaska, I guess, had a correlation with that area of new open ocean. But that is a really interesting idea, and I definitely would like to look into that further.
Okay, thanks. Thanks for a great talk.
Thank you.
Julie has a question next.
Yes, hi, Laura. Great talk. Good to see you. I was thinking to myself of the file drawers I have in my office that are black and white air photos taken by my predecessor, Joe Hartshorn, around the Greenland ice sheet. At the end of during the Cold War, they were looking for new places to develop airports on large flat deltas and different places. I could look through those, and if they could be of any help to a future graduate student, let me know, because I've always wondered what could be done with these photographs.
Yeah.
So just so you know that I have them, maybe sometime I can send you some pictures of some of those and you can see whether they'd be useful to someone.
Yeah, thank you, Julie. That would be fantastic. And
Great.
they're
Thanks.
such great photos to look at too, as well. They're just, it's such a fun data set.
Yeah, I was thinking of revegetation of some of these surfaces too, as climate warms. But anyway, I'll be in touch. Thanks.
Thank you.
Great. Do we have any other questions? Okay, well, I want to thank you so much for your time and for getting up so early. This was incredibly interesting.
Thank you for having me.
Thanks. Have a good morning.